So, our first speaker of the night is Professor Bill Warwick with his talk, The Unstable Atom. So, Bill is a professorial fellow at the University of Hampton and director of the Commercial Radioanalytical and Consultancy Laboratory at GAU Radioanalytical. He has over 30 years' experience in commercial radioanalytical operations and research working closely with the nuclear industry, government agencies and academic sectors. He started his career in UKEA Winthrop before moving to the University of Southampton in 1994. And in his spare time he plays the drums for a local rock band, and his favourite film is The Hangover.
I'll have to find out where that bit of information came from. Just whilst we're loading the slides, I'd just like to say I'm a little bit of a fish out of water here in the sense that I'm a chemist by background. I work in an ocean and earth science department, and I'm talking to a group here on a physics subject. So this is going to be a bit of an odd mixture. And what I wanted to do this evening was just give you a bit of an insight into radioactivity and really the radioactive world that we live in. So the group that I work for, most of the group I see is actually here tonight. The group that I work with, we specialise in radioactivity across the board, anything to do with radioactivity. And we use radioactivity as a tool. We measure radioactivity, we do research on radioactivity, be that in the environment or in industry. So that's our thing. And one of the things we find is that when we are talking to people about radioactivity, they see it as an artificial property. It's something which is man-made or has been created. And that's just not the case. We live in a radioactive world. And what I wanted to do was to give you some insight as to what that radioactive world is and why it's important to us as researchers. So what do you tend to think of when we mention the word radioactivity? Well, normally the things which come to mind are nuclear weapons detonations or the nuclear industry, nuclear power production. You might think of nuclear waste and the challenges of disposing of nuclear wastes. Or you might, if you're a Sky Atlantic subscriber, you might be watching the latest mini-series on Chernobyl, looking at this iconic nuclear accident. But how many of you would think of a banana? And what I want to get across tonight is why the banana is so important when we're talking about radioactivity. And what is the significance of radioactivity in our natural environment? So a little bit of background. Radioactivity, discovered by this gentleman, Henri Becquerel, in 1896. It was actually discovered completely by accident. So Henri Becquerel was working with phosphorescent minerals. He was interested in the properties of phosphorescence. And he was exposing phosphorescent minerals to light, sunlight, and looking at the effects on photographic film. And what he discovered, purely by chance, was that even when the minerals were not exposed to sunlight, he could still get some exposure on a photographic film. And that was due to the radioactive properties of the minerals that he was investigating. And this led to the discovery of radioactivity and the subject that we're now interested in. Now, I said earlier on that I'm a chemist. I have to put my hands up to that. So this is my sort of go-to, the periodic table. And within the periodic table we have 92 naturally occurring elements, all the way down to uranium at the bottom there. But when we're talking about radioactivity, we're talking about radioactive species, and we're talking about what we call radionuclides. And in actual fact there are far more radionuclides. And this is our, if you like, our periodic table of the radioactive world. And this is plotting all of the radionuclides on a graph where we're plotting number of protons against the number of neutrons. So each one of those little squares represents a radionuclide, and the black dotted lines running through the middle there are the naturally occurring stable isotopes of the elements. And everything above that in blue or below that in red are the radioactive isotopes. And radioactivity is really the process by which those unstable radionuclides are trying to gain stability. They're trying to get back onto that black dotted line. And that's the process that we're interested in. And when we're talking about radioactivity, we're really talking about the atom, we're talking about the nucleus, we're talking about the processes which are occurring in the nucleus. And the nucleus is quite a compact and quite a small part of the atom as a whole. Just thought I'd share this fact with you. I discovered it as I was preparing for this talk. But if you took the atoms from the human population, 6 odd billion people on the planet, if you removed all of the space associated with those atoms, you'd be able to fit what was left inside an atom. That's how much space is associated with an atom. And when we're talking about radioactivity, we're interested in the processes which are occurring within that nucleus. Bit of terminology now. When we're talking about radioactivity, we're talking about the process, we're talking about changes within the nucleus. And the radioactivity of something is normally defined in terms of becquerels. So we'll talk a little bit about becquerels later on, but a becquerel is simply one atom disintegrating every second. So if we have an atom disintegrating every second, we have 1 becquerel of activity. When that atom disintegrates, it can shoot off particles, or it can shoot off electromagnetic radiation. If particles, it's likely to be an alpha particle or a beta particle. If it's radiation, it will be gamma radiation. Those are our 3 main processes that we're interested in. So that's the radiation. The effect that has on us as individuals is measured in terms of dose. So we have radioactivity, which is the rate of change in the atoms, radiation, which is what's coming off, and dose, which is the effect on us, on our body. And dose is measured in sieverts. How do we know that radiation really exists? I'm hoping this will work. But this is a cloud chamber. And if you look at the piece of uraninite which is sitting in the middle here, and if you look to the top right of it, if I play that image again, you'll just see a white track, and that's an alpha particle which is being emitted from uranium which is in that uraninite, and it's travelling through this supercooled gas and causing condensation. And we can actually see the particle being ejected through. So I said a little bit about radioactivity, but what about the radioactive world in which we live? And this is the thing which I think is the key message for tonight, is we do live in a radioactive world. And why is it radioactive? Well, there are a number of reasons why we have radioactivity. If you think about radioactive materials, we're bound to think about uranium and thorium. Those are the common radioactive elements. They're the famous ones. In actual fact, uranium is very abundant, and it's about as abundant as tin. It's more abundant than gold, it's more abundant than silver, and it's more abundant than mercury. So it's quite common. But uranium and thorium are not the only radioactive things that we have naturally on the planet. In actual fact, radioactive materials are being produced all the time, and in the upper atmosphere we have cosmogenic radionuclides which are being formed by cosmic ray interaction on the upper atmosphere. And these include tritium, beryllium-710, carbon-14, aluminium-26 and chlorine-36. And these are being produced all the time. So these are constantly being supplied to the atmosphere. And from an environmental sciences point of view, they're really useful because they give us a marker by which we can track processes through the environment. The image on the right there is actually an image of an imprint that was taken from an Apollo astronaut's space helmet. And it shows the impact craters from cosmic radiation actually on the helmet itself. So as the cosmic particles were hitting the helmet, they caused these pits which have then been shown through this sort of putting a latex on and peeling it back off again. So quite energetic particles hitting our atmosphere. So we have cosmogenics being produced all the time. We also have what we call primordial radionuclides. And these were formed during nuclear synthesis and were present in the formation of our solar system. There are 286 primordial nuclides in total, and of those, 33 are classed as radioactive, so far more than just our uranium and thorium. We do have uranium and thorium decay to produce a whole string of other radionuclides. And this again is important from the environmental sciences point of view, because we can use this chain of radioactive formation in many ways in terms of looking at environmental processes. So we have a whole range of radionuclides which are present naturally, being generated all the time from uranium and thorium. Where do we find uranium and thorium? Well, the answer is pretty much everywhere. We find it in the oceans, we find it in our lakes and rivers, and we'll find it in the soil that you're walking on, the ground. So we're surrounded by uranium and thorium, and it's actually very abundant. Typical soil concentration, about 2 parts per million. If we look at the oceans, again, very abundant in the oceans. And if you actually look at the amount of uranium that's present in the world's oceans, how many times do you think you'd be able to fill St. Paul's Cathedral? Any guesses? 5 times? Any advance on 5? 10? Any more? 300. Any more? If you were to extract all of the uranium from the world's oceans and put it into St. Paul's Cathedral, you could fill St. Paul's Cathedral 1,300 times. That's how much uranium is in the world's oceans. And one big area of research which is ongoing at the moment is looking at how that uranium can be extracted for commercial and power generation purposes. And there's a program of work being undertaken in the States developing these sort of sponge-like materials which will just sit in seawater and will absorb uranium. And on the left-hand side there you can see the sponge is a sort of yellow colour, and that's because it's taken up the uranium from the seawater. So we have a vast resource, if you like, of uranium present in our oceans, and ocean mining is now seen as quite an interesting research area. We can do it for other elements as well. It doesn't have to be just uranium, so elements such as vanadium can also be extracted from seawater. But uranium is certainly one of the key ones. I feel safe going back to a periodic table. So if we look at the periodic table again, what other elements are radioactive? Well, we've seen that uranium and thorium are naturally radioactive, and we know that because of their decay chains, they'll also produce other radioactive species, so polonium, astatine, radon are naturally occurring radioactive materials. They're being produced from the decay chains. But you may be surprised to find out that there are other radioactive elements. So potassium contains potassium-40, one of the isotopes of potassium, which is naturally radioactive. It's actually quite an energetic beta-gamma emitter. And below potassium, we also have rubidium. Rubidium, again, actually quite radioactive. In the middle of the transition metals, rhenium actually has quite a significant radioactive emission. So normal, natural rhenium will be technically radioactive. And if we look at the lanthanides, then we have lanthanum, samarium and lutetium. Again, they have radioactive isotopes which are naturally occurring, they're long-lived primordials, and they will be quite easily detectable if you try to measure the radioactivity. So we have all of these species around which are contributing to the radioactivity that we see in the environment. So how does that affect us? Well, in actual fact, because of these radioactive materials, these radioactive elements in the environment, these can be absorbed by the foodstuffs that we eat, and therefore many of the foodstuffs that we consume are naturally radioactive. One of our areas of interest is the amount of radioactivity in foodstuffs and how that can contribute to individual doses. So on the top of the list in terms of radioactive foods, we have Brazil nuts, 444 becquerels per kilogram, so 444 disintegrations every second per kilogram. We have potatoes at 125 becquerels per kilogram, and we have our good old banana at 130 becquerels per kilogram. So actually quite reasonable levels of activity within our foodstuffs. And these are all radioactive because they contain predominantly potassium and the potassium-40, or radium, radium-226. And that's coming from the uranium. In the water we drink, quite amusingly, tap water is quite heavily processed, so it tends to be relatively low in radioactivity. But if you go to bottled waters, which are marketed as being much more pure and straight from the water supply, they can actually contain quite high levels of uranium. And some bottled waters have been measured up to 6 becquerels per litre of uranium. So quite high concentrations of activity in the foods and the water that we're drinking. What about the building materials that surround us? Well, you're probably all aware that granite is radioactive. So if you have a nice granite worktop in your kitchen, that's going to have quite a nice radiation emission from it. But also concrete actually contains quite a lot of radioactivity. Brick. Most plasterboards, or if they're not manufactured from natural gypsum, if they're manufactured from byproducts from the phosphate manufacturing, they'll contain quite high levels of certain radionuclides. And also fly ash, which is used to make breeze blocks. Again, that's concentrated down during coal burning and can contain quite high levels of activity. As well as radioactive materials in the environment, we also actually have examples of natural reactors. So we think of reactors as being man-made, but in actual fact, there is an example of a natural reactor in the Gabon in Africa. About 1.7 billion years ago, the conditions were just right to concentrate uranium into a shape that would allow criticality. Water flowed through, which allowed moderation of the neutrons, and we actually had a nuclear reactor. There's a lot of evidence for this reactor operating for millions of years. It operated at about 100 kilowatt power. So it wasn't insignificant. And this is important because we actually have a natural analogue which can be used to look at the fate of radionuclides in a geological environment. That's important for waste disposal. So if we're trying to look at how our radioactive waste might behave in the environment in the future, this actually gives us a natural analogue. And it actually shows that over the lifetime of this reactor, the radionuclides didn't move that far. What's the effect on humans? So, I said we live in a radioactive environment, but we want to know what effect that has on us. And to do that, we need to know something about dose. And we measure dose either externally, which is radiation shining up to us, or internally, which is where we either consume radioactive materials or inhale them. And we measure this in terms of SIEVA. So to give you an idea, your typical human has been bombarded on average with about 400,000 cosmic ray events, 100,000 neutrons from space, about 200 million gamma rays from the soil, 15 million potassium atoms decaying in your body, 7,000 atoms of uranium, and about 30,000 decay events from radon every hour. That's what you're being exposed to typically. So you're living in quite a radioactive environment. Where do you get your dose from mainly? Well, typically, can't see the number there, but about 13% of your dose comes from the soil, about 50% of your dose comes from radon inhalation, about 12% comes from cosmic ray exposure. 9.5% is coming from the radionuclides which are internal to you. 15% on average from medical exposure. Industrial weapons fallout, quite small contributors, about 0.2 and 0.5%. And that gives you a total dose of about 2.6 millisieverts per year. So that's what you will get on average in the UK just from natural radiation. It does vary though as you look around the country, and you can see that if you're living somewhere in Cornwall or in the Midlands, then the radiation doses can be higher, and that just reflects the underlying geology. Just to give you some doses in perspective, so we say that the natural background is about 2.6 millisieverts per year. You'll get doses somewhere around about 0.001 millisieverts from your bananas, so that's even 10 bananas. Dental x-rays are a little bit higher, chest x-rays around about the 0.01 millisieverts. Flight from New York to LA, that will give you a radiation dose of about 0.02 millisieverts. And that's because you're flying at altitude, so you're being more exposed to cosmic radiation. Going up the scale, 2.6 is the UK's average. Limit for a radiation worker is 20 millisieverts in a year. We estimate that in the Litvinenko case, he was exposed to around about 5 sieverts of radiation dose. So that gives you an idea of the high radiation doses that he was being exposed to. So how do we use natural radioactivity? We live in this naturally radioactive environment, we have all of these traces, and basically, from an ocean and earth point of view, we can use them for many, many things. So we can use them for air-sea exchange, we can use them for short-term ocean circulation studies, ocean water mass movements, concretion growth rates, sedimentation rates, and dating of biogenic carbonaceous materials. I'll just give you a couple of examples. This was some work done by a colleague a few years back now, but this was looking at tritium and using it as a tracer for ocean circulation. And what you see is that tritium is deposited on the surface of the oceans and then is drawn down at certain points in the ocean to deeper waters. And because we know that tritium is being constantly produced in the atmosphere, it's a 12-year half-life, then we know that if we're seeing tritium at depth, we can get an idea of how long it's taken to get there. If we look at the natural decay chains, then different radionuclides within those decay chains will have different properties. So some of those radionuclides will be atmospheric, they like to fly. Some like to sink, some like to associate with sediments. So we can look at those decay chains and we can see how they're being perturbed. And we can use that to get an idea of what processes are going on, and quite often the timescales that those processes are occurring over. So again, we can use the primordial radionuclides for a number of different types of application. I'll just talk about 2 in particular. So one of the things we're particularly interested in is looking at scavenging of particles from the ocean upper layers. And what we find is that uranium likes to be in solution, it likes to stay in the water column, but it decays to thorium. Thorium doesn't like being in the water column, it likes to associate with particles. Now, all else being equal, we'd expect the same amount of uranium and thorium, uranium-238 and thorium-234. But what we see is this depletion in the surface layers of the ocean, and that's because the thorium is being scavenged by particles, and those particles are sinking. And we can use that to work out particle fluxes and particle movement. We can also use the lower end of the decay chains for looking at sedimentation rates. So in the uranium decay chain, one of the decay daughters is radon. Radon is a radioactive gas. It gets released into the atmosphere. And it decays to lead-210, and the lead-210 will drop out and sink onto sediments. And if we look at a lead-210 profile down through a sediment core, we see it highest at the top of the sediment, and then as we work down through the sediment core, it drops off. And we can use the shape of that profile to work out the age of the sediment. Why is that important? Because we can look at sedimentation rates, we can look to see how the morphology, geomorphology of an area is changing. We can also look at sea level rise, that links in with climate change and such like. So these are areas where we can use our natural radionuclides as tools. So, very brief overview. Really just to say, we do live in a radioactive environment, we're surrounded by radioactivity. When we talk about radioactivity, we should be putting it into that context. However, it is also an incredibly useful tool, and we can use it to our advantage in many, many studies on the environmental side. Thank you very much.
Thanks to Professor Bill Warwick there. So we have about 5 minutes for questions. So does anybody have any questions, Phil, on anything you've seen in the talk, radioactivity, science, anything like that? Yes.
The natural the natural reactor in Africa, what did that actually cause, or did it just go about its business not really doing anything?
That's a very good question. In actual fact, the natural reactor in the Gabon was self-regulating, because what would happen is that you get water flow which moderates the neutrons, so it slows the neutrons down. And you need the neutrons to slow down before you can get fission in the uranium. When you get fission, you generate heat, the heat boils the water off. You lose your moderator, the reactor shuts down. So basically what it went through was a cycle of heating and switching off. throughout for a few million years. So it didn't actually do anything as such. It generated fission products. Those fission products have been found local to the ore deposit, so we know they haven't moved very far since the reactor was operational. And when you think that was, let's say, about 1.7 billion years ago, that we're looking at a very slow transfer of radionuclides from that point, which is why it's interesting from a waste disposal point of view. But literally for the millions of years it was operating, it would just switch on, switch off, and go about its business. It's the only example that we're aware of at the moment of a natural reactor, because you have to have very specific conditions which conspire to give you the correct conditions for the reactor to go critical. And I think it's one of the misconceptions is the idea that like a nuclear explosion is an easy thing to create. And you have this image of a nuclear reactor exploding with a mushroom cloud. That really can't happen. You can get a conventional explosion on a nuclear reactor, which is what happened with Chernobyl, 3 Mile Island, wind scare. But you can't get a nuclear explosion because you need very specific conditions and for that to occur.
Great, thanks. And so does anybody else have any questions for Phil?
So what you were using for the dating in time, presumably that assumes that the atmospheric levels are stable. Are there examples of instances where that's going to shoot up or drop?
So the example I gave you there was for lead-210 dating. Lead-210 is a 22-year half-life, so it tends to be a relatively short time period. You will get conditions locally which will affect the flux of lead-210 through the environment, and that's what we'd have to correct for when we're looking at the profiles on the cores. But that's sort of one of the ways you'd have to adapt the model to account for any changes that are likely to occur from different inputs coming into the system. If you're looking at longer term, for example carbon-14 dating, then yes, there are many factors which could affect the carbon-14 production rates. There are solar cycles which will do that. There's an input from weapons testing which will affect the carbon-14 inputs. And one of the challenges with carbon-14 dating has been to correct for all of those different factors which are affecting the rate of C14 production. So and that's quite advanced now, but it does take quite a lot of work to make those corrections.
Thanks. And we have time for maybe one more question, if anybody has any. So, is anyone? No? Okay, great. So now we have a quick break for people to get drinks, order food.